So how many of you in the audience have actually worked in an embedded company in your careers? Show of hands. There's a few of you. We had an open space yesterday, and it was quite interesting because there's about 5 or 6 of us, and we knew we were in the right space because that's us, right? We are a minority in this community. So my talk today is about how DevOps principles apply to embedded software and kind of what we're doing at Navico, which is where I work at the moment. So a little bit about myself. I didn't put a lot of stuff on this slide, but I've been in consumer electronics for most of my career. I initially started at Navman when they were getting into vehicle navigation products, and then since then have gone through a number of different products with Navman, and then at Navico, I'm currently working on a number of different initiatives as well. That's what I looked like when I started my career in embedded. You can tell there was a transformation there, and it's pulling out your hair is not uncommon. So just to give you guys a bit of a perspective on some of the things I've worked on before. So I've done smart watches. We've done vehicle navigation products at Navman, various different kinds of them. The one in the middle, the one that looks really weird and old, was probably the first car navigation product that was sold in New Zealand. And that cost about $2,000 at the time. So things have moved on quite a lot since then, but the problems in embedded are the same, and the solutions for them are fairly similar as well. So I'm at the moment at Navico, and we do some of those marine products that you can see at the bottom. They look like high-tech tablets, but they are special built products that work in embedded environments. So what are the challenges that we see in embedded that may be different to what the rest of you guys see in your industries? The first one is hardware, and dealing with hardware is a completely different set of problems when we talk about hardware in traditional software development. So for us, hardware involves smaller computers, microcomputers, and there's always resource limitations in them, whether it's CPU limits, whether it's memory limits, and we have to deal with it, right? We just have no choice but to make our software work well on the hardware platforms that we run on. Debugging. Now, debugging software is hard enough. Throw on top of that problems that are caused by the operating system that you don't know at the start, problems that are caused by the hardware because you're working with a team that's still doing prototype hardware, right? They're still trying to figure out what components work well. And then there are these bugs that I call UFO bugs. They're quite common in embedded. There are the bugs that come and go for no reason. You could have a product that works perfectly today, and you take it out into the external environment, and it suddenly stops working. We've had an example of this quite recently with one of Navico's products. We have high-end touch displays, and these are marine certified, so they work when there's water on top of them. And we had a customer in Italy whose product was just not working. When they were trying to touch it, it just wouldn't work. And we tried reproducing this problem in the lab, and you have lots of engineers on it. It's a very prominent customer, happened to be selling a boat to a MMA fighter, a very high-profile customer in the end. We just couldn't find a fault with it. We went through every single product we had, every single software version, to find that the boat that this was installed on was in Italian summer and was getting slightly hot. And there was a component that the factory had chosen to not replace on that piece of hardware that is failing under high temperature. How do you fix a bug like that in software, right? So you can't. And most of the developers who are trying to tackle these problems are used to using oscilloscopes and JTAG connectors and things like that you wouldn't dream of doing if you're doing traditional software. And I mentioned briefly about the environment. So there's environmental factors that affect the operation of the software, but there's also things that we need to think about when you're writing software, whether it's to reduce the heat output from the piece of hardware you're working on, or whether it's handling moisture, especially if you're in the sea, and power consumption, which is an important point for anybody who has a mobile phone, right? And then there's deploy into production. For us, that word means a completely different thing. That's a factory, and our software actually goes to a factory to go into a piece of physical hardware that gets shipped to customers. Now, what this means most of the time is that the cycle times are quite small. Even if you are connected to the internet and you can push software updates to your end consumers, in some industries, that's not really practical. So for us at Navico, most of our customers are in the middle of the sea. when they're using their products, right? They come to the marina once in a while, but most of the time they're on the sea. And most customers don't even know that they can do a software update. The demographic is slightly different. So how do you deal with that? How do you deal with being in a situation where your deployment to production is gated by a 3 or 4 month cycle? To put things into perspective, imagine if you were deploying all your infrastructure on AWS or Azure, and you were told that you only have access to your servers 3 times a year for a period of 1 month. Go. All hell will break loose, right? And that's a reality of some of the problems we deal with. So why this talk? Obviously for us, both at Navico and my previous companies as well, we wanted to find how we can improve the way we do software. And the general software development methodologies and principles are all still valid, right? It's still software. So how do we find ways in adapting what's being discussed, what's being taught, what's been learned in the industry into what we do in embedded? And what we've found is, or what I've found in my career, is that when people talk about new tools, new techniques, it feels a lot like an Olympic sprinter talking to another Olympic sprinter about how they're going to optimize their startup speed, how they're going to get their frame right, how they're going to exercise more, get their proteins, get their work routines to be better at what they do. And we sit there trying to crawl. And it feels like it doesn't apply to us most of the time. And that's the challenge. The terminology, the words, the infrastructure, the conversations are sometimes hard to translate. And the question you get asked a lot is, does this stuff even make sense for embedded? And they do. So for me, looking at the principles of DevOps and the CI/CD mindset, there are some key things that I want to draw to your attention who are in embedded, and things I think are quite relevant to the industry. So high frequency, so being able to release software to customers faster. Reducing overheads. You always want to make sure that your software development is as efficient as possible. Improving defect resolution. Want to make sure that you find problems faster and fix them faster. Automate the heck out of everything. Who wants to do manual software development, right? And reduce the response times. So all of these are equally valid and I think equally applying to embedded. So what I'm hoping to do today is briefly do a bit of a case study on what we are doing at Navico. And to make it clear to everybody, we are still crawling, but we are starting to learn how to walk. So some of you, it might seem like these are very obvious tactics, but for those in the embedded space, hopefully it'll give you an idea on what you can achieve and what you can do. So Navico, as a company, targets 4 different markets predominantly. So we have 3 main brands that we sell in different regions. The first one is Lowrance, and we do a lot of these smaller fishing products. So these go on low-end boats, usually freshwater, and they have this little underwater sonar so you can find your fish. Very simple product. Then we go into the recreational marine market, which is your yachts and speedboats and things like that. A lot of these are the Simrad brand, and they have got much, much higher capabilities. So you've got these big touchscreen displays, you've got multiple different functions, charts, 3D underwater displays, radar capability, etc. And then you go into the sailing space. A lot of the America's Cup boats, you would have seen similar technology on them. So they're very simple displays with single values like your wind speed and your wind direction that helps the crew. And then you go on to commercial vessels, which are pretty much your big sort of cruise ship, container ships, cargo ships, things like that, which have a much more complicated bridge and a much dense number of equipments on them. So as a company, we are quite spread out. We have our main R&D center in New Zealand, the largest R&D center, but we have R&D sites around the world. We have our own factory in Mexico, so we do all of our, or most of our hardware development on site. But the development is spread around the world is the key thing. So what were our challenges? So we have a code base that services most of our products. That's about 5 million lines of code. And we actually support 61 products as of now simultaneously from the same code base. And that's a challenge, because when I say products, we are talking about hardware variations as well. So it's not just configuring something different, it's also supporting hardware changes. And what we noticed recently is that the growth in demand for our products is growing exponentially. So this is some real data from the last few years worth of software releases and the number of new products that we added onto our fleet. And you can tell that it's an exponential growth. And part of the reason for this is that unlike a cheap piece of electronic or a software that you can update frequently, most customers who spend 5-10 grand on electronics for their boat, they don't tend to update them that frequently. So customers who are building, or boat builders who are building multiple different vessels of the same configuration, tend to want to purchase the same hardware we had earlier. So the end of life requirements is not as strong. So the things tend to last a lot longer. And we can't really keep up with this graph, right? We're struggling already and it's exponentially growing, and you just can't hire people to keep up with it. That's not the solution. And the end result of all of this is that sometimes code just makes it out into the wild. And we have people who, like me, are starting to lose their hair just trying to keep up with the quality control and being able to control the release cycle of products. The other big challenge we've had, which I think is fairly unique to us, maybe not entirely unique, but rather than dealing with a single product, we almost always deal with a network of products. You saw some of the pictures that I had where there are a lot of different electronics on the board at the same time, and all of these are connected together either through Ethernet, through Wi-Fi, or through our own CAN bus protocol. And that makes software debugging and software support quite difficult, because you no longer control each individual piece as a whole. You could have somebody have one version of software on one piece and another on another, and the network should still work together. So the backward support, the compatibility of APIs is quite important, and it's very hard to change something once it's gone out into the wild, because you could have those products sitting on an old version for a little bit longer than you expect. The other big challenge we had is the architecture. So as a company that's been around for a long time, and been around since a lot of the modern development methodologies really started to catch on, we have a very old code base that was written by a lot of people who are writing traditional embedded software. We've had to maintain backward compatibility with older hardware, which has meant that it's quite difficult for us to go back and change some of that underlying architecture. We always have demand to support new hardware, so we also need to make sure that we extend the functionality. And if you do that without refactoring and fixing up your code as you go, you end up with much bigger code, much bigger mess than what you started off with. And we also have a desire to keep providing functionality for all of our customers. So those 61 products, we support those in the field right now. When we do a software release, we expect that to work on all of them and the features to work on all of them, which makes it very difficult to make significant change. So what does this mean? Defects were found late. Things were getting too complicated. We just couldn't find the bugs early enough. We didn't have a good way of using our manual testing process at the moment to keep up. And what that meant in terms of cost, the longer you wait to find a bug, and I think this is true in every industry, but more so in embedded, the cost of the bug is quite high. And what do you mean by the cost of the bug? If you're validating a piece of software that's been worked on and then more features added onto it, and you're finding the bugs at the very end, you're going to have compounding bugs, right? You're going to have bugs built on top of bugs. You're going to have bugs that have impacted other features unknowingly. If you're working on a hardware platform, you're going to find faults with the electronics on the boards right at the very end, after it's gone through validation. So it becomes quite expensive to organize for an organization to manage. Stabilization was a thing, and it was taking a long time. So in a traditional waterfall development methodology there, you finish your development and then you try to stabilize your software, right? And that process just wasn't working. It was taking far too long. And as I said, the manual testing just couldn't keep up. So the lost opportunity cost is something that people don't think about too much, but we have always had a desire to move in different directions with our software, to change the way we do our products fundamentally. But if you're spending all of your time working on fixing your current products and current software, your capacity for innovation just drops off a cliff, and it becomes non-existent. And that was the outcome of all of this. To give you a bit of a perspective, so we do a lot of analytics on our data, and this is a graph that tries to show our overall bug count coming down over time to do a software release. And what you can see with the orange line there is the bugs that we consider must fix. And these are issues that are new to the product or things we think are affecting customer safety. The blue ones are the overall bugs that have been found in the product by our QA team. And you can see there, sometime in the middle, there's a big drop in the blue line. And that's when we throw our hands up and go, we have to release this thing. Let's just get rid of all of these things. We're not going to work on them. And that's no good, right? Because that's your innovation. That's your continuous improvement. We just thrown away. And the focus then is to fix the most important issues, and they tend to have a long tail as well. Because as I said in the start, we are finding them late, and they're harder to debug at that point, because you don't even know what caused that problem to begin with. So for us, we looked at this in a more abstract way a few years ago, and looked at ways in which these problems can be solved. And obviously, CI/CD provides answers to all of these problems in different ways. But the common thing you hear, and you hear this from management as well, you hear that it sounds great, but it's not going to work here. There was a very interesting talk at DevOpsDays in, I think it was Seattle earlier this year, by a guy called Jess Humble, I think. And this was the title of his talk. And he talked about how a lot of organizations just put their hands up and say it won't work in their industry. And embedded is definitely one of them. So we looked around for case studies and for inspiration and help. And one of the most common ones that we found, and I think it's worthwhile for you guys in embedded to have a look at it, is a case study from Hewlett-Packard. So I think everyone's heard of this, right? If you're in embedded or you are looking at how DevOps applies to places outside of standard software development, you would have heard about the DevOps transformation at HP. So we spoke with Gary. He's one of the authors of that book, and he used to be the director of engineering at HP for this division at the time. And we came up with a plan on what we wanted to do to help our own development process. So the first one was tools and architecture. So let's fix that. Let's make sure we look at getting integration better with all the different tools we have available, and look at flexibility, and do that over the traditional kind of things that the embedded tools were offering us, which was compliance to process and making sure that we control things a lot more. Improve the build speeds, that was fairly obvious, and I'll talk a bit about why. Automated testing, that was a given. We just couldn't keep up with manual testing. And quality controlling incoming code. Make sure we stop bugs from getting in as much as we could. And all this was backed by data, right? And I think Alison gave a good talk about this yesterday as well. You can't do anything unless you have data to back it up with. You don't know what you're fixing if you don't have a way to measure if your fixes are working or not. So you'll see a bit of the data kind of thrown in there as we go. I'm not going to go into too much detail there, but hopefully touch on the key things. So we started off improving our tools, and I'm not going to name the vendor because they might actually be in the audience. We had a VCS which was very much old school, in the sense it was designed for having strong process around who gets to commit what, strong process around isolating code, strong process about how code actually makes it to mainline. And it was very much proprietary. It was very limited in terms of its integration into other products and tools. It had very limited CI support. I don't think CI was even a term they had known about at the time. And it didn't have any way of reviewing code. So our code reviews at the time were a guy walking up to someone's desk and sitting there and reviewing what they've done and see if that was good enough. So we moved to Git. Yay, Git. Which sounds trivial and sounds obvious, but it opened up a whole lot of opportunities for us as a company. Obviously, code reviews were much better. We could integrate with Bitbucket's code review system. Integration with CI, everybody does Git now, right? And CI is part of the deal. And it was fully supported on all all the tools we were using. So everybody loved it, and that was great. The architecture piece was harder. We had some wins already. So we had a very configurable code base from a very long time ago. And what that meant was we could do that single code base for 61 products. And that is a great start. A lot of companies who are in this space do not have that. So if you're looking at going towards a CI model, make sure that you start there, right? Make sure your code base is actually configurable depending on the hardware platform that you're running on. Our hardware platform also wasn't too bad. We had a separate processor card that went into a daughter card that went into the different products. That meant that most of the time, although we had 61 variations, the hardware platform only varied much less, maybe about 9 different variations. And we also already had runtime feature flags. Great, right? We weren't actually using it for the purpose that we were going to use it for, but we had the ability to turn on features and turn off features using configurations. What we didn't have, we had lots and lots of cyclic dependencies and cross-dependencies across the code base. And we wrote some tools. So you can't actually see the details here, but one of our software engineers decided to write a tool that generates this web page. And this web page shows the cross-dependency between each of the modules. So this was our starting point. We had some data. And the plan was to make sure the line underneath that diagonal was all clear. And we managed to get that in about a year and a half of work. So that was a good start, right? So what does that mean? If you don't have cyclic dependencies in your code base, it's much easier to test things in isolation, and you don't have to worry about what the impact might be. Singletons was another problem. So this is a bad concept that we see in a lot of embedded software where people want to access certain pieces of hardware or certain attributes of a hardware, and you write a class to handle that, and then you use it from everywhere. You point directly at it. That's bad. And we also wanted to promote unit testability, and you can't do that with singletons, obviously. You want to have units of functionality that you can test independently of everything else. So that's something we focused on as well. And that was our branching strategy when we started. And this was partly driven by the tool that we used. So we had many, many long-lived branches. And our testing team were testing each one. People were scared of breaking things. So things were kept in isolation. And what happened at the end, you'd merge all your code back to your main line and everything would break. So you'd have a large stabilization period at the end just to get your code base back up to where it should be. So we changed that. We went to a single branch model. What that meant was we were doing smaller batch sizes. We were using our feature flags. Features that weren't completed were put into the code base, turned off. And the validation was focused on a single branch. So we haven't talked about automation here. Even before we got to automation, having your manual testing team focused on a single code branch meant that they actually get much more coverage across the code than they would have spread across 5 or 6 different branches. So even without automation, this actually helped quite a lot. Build speeds. Who here has this problem in the organization that compiling code takes a long time? Yeah, the embedded guys put their hands up, right? So here's our statistics. So it was taking us 8 hours to build our core OS code base, an additional 2 hours for each application that was on top of that. So a typical software release was taking 14 hours to complete. And we had one guy over there who was responsible for making sure this comes out on time. And what that meant was when he goes on holiday or he goes home after finishing work, get a phone call. It's not out yet. Can you fix it, please? And that was no good. So we looked at a couple of options. The obvious ones are to increase your build speed, right? And you throw whatever technology you can at it. You might throw additional servers at it, and that wasn't really viable for us. Parallel builds, yeah, that's great. You need to re-architect the code base in a way that allows you to do parallel builds. What we found worked fairly well is for C++ code anyway, and there might be different tools for depending on the industry you're in and the languages you use. Ccache works really great. It's a caching system that caches your object files. So our builds were incremental now, and they're taking significantly less time. Incredibuild, it's a commercial tool. We've been playing around with that, which distributes your compilation across everybody's desktops. So if you have 100 developers spread around the world, you can use 100 desktops to build rather than one mainframe. And DiskCC, which is an open source version of that. So what we found with this is that our average build time dropped off a cliff. So that we were taking around 4 to 5 hours to do an incremental build on our build system to verify a code change, and that dropped to an hour or so. And that allows a lot of things now, right? Because if your builds can come out faster, it means you can do your automation earlier. It means you can get feedback earlier. So this alone had a big impact on the rest of the system. So test automation was the next area for us to tackle. And this sounded great because test automation is something that everybody does. It's not new. We wouldn't have to think about anything unique, right? So that's what we found when we went looking for test automation tools and frameworks, and none of it really worked for us. That's a typical example of what a test setup looks like for us in Navico. So poor old manual testers will have these set up everywhere around the office. You have your multiple displays, your keyboards that control it. You have single switches to turn on and off certain functionality. And it gets even more complicated when you have to try and debug hardware that hasn't even got a physical case developed yet, right? So the environment we were trying to work under wasn't really supported by a lot of the test automation tools. They were designed around a typical use case that wasn't really relevant for us. So what did we do? So we said, let's start with what we can. Let's start with micro tests. So we started doing unit testing. And that's easy to do. You're doing unit testing. We had a Windows simulator. People were using Visual Studio to write code on a Windows PC. This is easy. And then we found that unit tests might pass on a Windows PC but fail on the real hardware due to timing issues, due to other problems that you might have. So we said, why don't we do unit testing on real hardware? So we built a farm of real hardware. We built some in-house scripts that takes the executables that have been built for that platform, finds the right piece of hardware, runs the unit test on the hardware, gets feedback, and then tells the developer if the unit test failed. So this was great because now developers didn't need to worry about the different hardware variations. They could just push their code into the repository and it would do the work for them. And we looked at tools. So we already had some tools in-house. The networks that we worked in was quite complicated that we couldn't really simulate everything, but we had in-house simulators that allowed us to simulate certain behavior. So the remote controls that we use talk through a CAN bus protocol. We can write a piece of software that'll do that. The N2K, which is the CAN bus, we had a software program that could inject data into that. Again, a software solution to a hardware module. But we also built some hardware modules. So that big box on the left is actually a product that we do in our own factory. You can't buy this off the shelf, but it's a piece of hardware that allows us to mimic sonar data coming from a transducer. So if you want to test your software without being in the sea, on the side of a boat with a transducer plugging under the water, we can now simulate that data with a piece of hardware. The thing on the right is a small utility that we had been selling to end customers for upgrading their software over the CAN bus. It had USB and CAN. We can repurpose it. We can now plug this into our PCs and inject data using the same interface. We don't have to build it. We can reuse it. So we looked at finding what we already had lying around and tried to reuse that to help with our infrastructure. So my advice, if you're looking to sort of build or buy, is to look at what you can do with what you already have, and look at functional testing and API testing instead of trying to get into the details of how do you simulate everything you can do. We ended up using a third-party product, which I haven't put in there because it might not be relevant for your industry. But we ended up finding a third-party product that allowed us to control our UI using a PC or a Linux simulator, which meant that we could run this now on real hardware. And I'll show you guys a little bit of that. And the other big problem is we couldn't run the test suite that we wanted to run on a piece of hardware in a reasonable amount of time. So to give you guys a kind of a bit of an example, we had about 10% of our testing coverage done in automated way. And that was taking about 6 hours to complete on real hardware. And imagine if you had 100% coverage, right? You're looking at 60 hours of automation, and that just wouldn't work. So try to figure out what your smallest build acceptance tests are. Find a subset, run that periodically, and then maybe you can do your full regression sweep later. So here's an example. Hopefully you can see kind of how this thing works. So we have a PC that executes the tests, and you have a piece of hardware there that's being controlled by it. And in parallel, the PC is controlling that box, which is emitting the right kind of signals on the network, and the hardware is now picking that up and verifying the functionality. That test would have normally required someone to go onto a boat and go onto the lake to do, or the sea to do. And you can now do that on a bench quite quickly. So that's the kind of thing you can achieve. So our pipeline now looks a bit like this. So we have code commits. They create a pull request. We have automated builds. We do our unit testing on that, on real hardware. We merge code to the master branch directly. And we run daily integration builds at the moment for master. So we build all of our hardware platforms, and we build all of our application variations. So QA every day has a build that's ready for verification. So what's next for us? We talked a bit about configuration as code for deployment pipelines. For us, it's mainly around actually setting up our build environment. We may not have a complicated delivery network on the other end, but we do have variations we always have in hardware that we want to be able to write in code. So we don't have to have one of our DevOps people go and have to change a Jenkins configuration. We are looking at code quality tools as well, which would help a lot with this. So there are third-party tools out there that help with checking your architecture, checking your code structure to make sure it's actually good. So we're looking at that. We want to simulate hardware a lot more than we do at the moment. So take out every piece of hardware that's impacting your ability to test on a simulator and replace that with a piece of software. We also want to get to the point where we have a completely simulated environment for our developers so that you don't have to have that piece of hardware on your desk to verify a bug. A common problem would be that a QA person finds a bug on product X and the developer doesn't have that product or can't simulate it on their simulator. So we want to get to a point where we have a complete simulation package with everything that developers can use. And we want to scale. We want to move our infrastructure, our build infrastructure, automation infrastructure onto the cloud. And this is where we're struggling with knowledge, right? And this is why kind of help. We are crawling over there. If you guys can help us walk, it'll be great. So my team's sitting on that table over there. You can see them. You can't miss me. Come and talk to me afterwards if you think you know what we're doing. So what we want to do is we want to add those yellow pieces to our pipeline soon, right? We want to get full UI automation tests going. We want to have architecture checks going. And we want to get to the point where we are doing full automated UI test coverage at the end and having our product ready for release at the end of it. So we may not be able to deploy to production every hour or every day, but we want to be in a position where we have something available for the factory to pick up when they want to. And we can give our customers if they want to install it. So I'll quickly finish with some lessons that we've learned, and hopefully you guys can take some away from it. I didn't talk a lot about culture, but culture is really the number one thing to think about. The reason I didn't talk about culture is the problems with culture is common. I don't think there's anything that's unique to embedded software in terms of fixing your culture. So think about that. You need to make sure you are in an organization, not just on the development side, but overall, that's buying into the idea of improving your processes and improving your delivery timeframes. Collect data. I think we've had lots of talks about that. You can't do anything without that. And to get executive buy-in, that's usually what you need. For us, the data wasn't purely how fast we can do a build. It was more about how much inefficiencies we have, how much time are we wasting from developer time where they could innovate that we're spending instead fixing bugs. So execs, as we've heard before, don't care whether you're building it in 2 hours or 1 hour, but they do care about where we're losing on money, right? When it comes to the dollars, they care. Don't be afraid to change your tools and processes. Just throw them out if they don't work. And test automation is absolutely the key. It doesn't matter if you're in embedded or if you're not in embedded. If you don't automate your testing, if you rely on people to find the bugs, you're never going to get to the point where you want to be. So invest in hardware if you have to. Build your own. Virtualize as much as you can. And the key thing is focus on good software design for all of that. Don't hire somebody who's going to automate your testing because they've done some Python in the background a few years ago. Hire software engineers to do this, right? Make sure it's properly architected so that it can scale with your needs.